Hello, good morning, everybody. So now we are continuing our online sessions with some of our derivations. So far we have completed all our remaining theory portions. So we have a few derivations related to the compartment model is remaining. So today we are discussing about the two compartment open model IV infusion. So hope you remember something on compartment model and what are the topics we have completed. So far we have completed one compartment open model IV bolus, IV infusion, extravascular. Along with that, we have completed Wagner-Nelson method, then urinary excretion method, rate of excretion, sigma minus method, and we started the two compartment model. We completed the IV bolus, two compartment open model IV bolus also. So under the two compartment we have two pending topics, that is IV infusion as well as extravascular. Okay, so let us see what we have discussed in the last session, Sandro. Okay, so IV bolus we learned. IV bolus we know that was mono exponential form, and we determined the rate constant, rate of elimination, that is elimination rate constant Ke we have determined. In the IV infusion also it was a mono exponential form. There we have determined two rate constants, that was rate of administration as well as rate of elimination. These are the two rate constants we deal with IV infusion in the one compartment. And in extravascular one compartment it was a bi-exponential curve we obtained. There we studied about the two rate constant, that was rate of absorption as well as rate of elimination. So in the one compartment we deal only with maximum of two rate constants and maximum of a bi-exponential one. In the two compartment model, IV bolus itself, it was a bi-exponential one. There we dealt with three rate constants, that is K12, K21 as well as Ke. So three rate constants we have seen in the two compartment IV bolus. If we compare with the one compartment IV bolus, there were only one rate constant Ke, where here we have K12, K21 along with Ke. So in the two compartment we learned the drug is initially distributed into the central compartment, and from the central compartment it is distributed into the peripheral compartment. So there is an addition along with that elimination rate constant for elimination, there is a rate constants for distribution also. Okay, so now we are going to discuss about the IV infusion. So we need to learn IV infusion and extravascular in this chapter. Okay, so today onwards we'll be discussing along with the video. There will be some questions will be asked to you people. You can answer in the Google Classroom itself. In the comment box you can answer those questions. Okay, so as a revision, the first question is the Akhila can answer. So what was the nature of the graph for an IV bolus? Okay, what is the shape of the graph for an IV bolus, one compartment IV bolus? And Anjali Shaju can answer, what was the difference in the graphical representation of a IV bolus for one compartment and two compartment? What is the difference in the graphical representation of IV bolus for one compartment as well as two compartment model? And Dheema can answer, what is the graphical representation for extravascular? What was the graphical representation for extravascular one compartment? Okay, now this was graphical. This is the representation of schematic representation of one compartment IV infusion. We have rate constant, rate of administration R0 as well as rate of elimination Ke. And this was the graphical representation of plasma concentration against time we have plotted. So two graph you can see, and it attaining a steady state concentration also. The first graph with a lower concentration, and the second graph is with the double the rate of administration. The first was the rate of administration was R0, and the second one the rate of administration was double to 2R0. So this was the graphical representation for one compartment IV bolus. Okay, just telling for reminding the things, that's it. Okay, now this is the two compartment open model IV infusion. So we have two compartment. One is the central compartment, other one is the peripheral compartment. Towards the central compartment, the drug is administered at a zero order rate, that is R0 towards the central compartment, and from the central compartment the drug is moving into the peripheral compartment at a rate of K12, and from the peripheral compartment the drug is redistributing into the central compartment at a rate of K21, and the drug is eliminating from the central compartment at a rate of Ke. So here we have four rate constant, that is one rate constant for administration, another rate constant for elimination, another two rate constants for distribution. Okay, now the question is, Gautam, you can answer. The distribution of drug from central compartment into the peripheral compartment depends on what? The distribution of drug from the central compartment into the peripheral compartment, that is the rate constant is K12. K12 is depends on what? As well as K21, that is drug distributing from the peripheral compartment into the central compartment, depends on what? Now, so in the IV bolus we learned the rate of presentation of drug into the body. Okay, so the rate of presentation of or change of plasma drug concentration in the central compartment, change in the plasma drug concentration in the central compartment, that is dC by dt, that is equal to R0 minus K12 cc plus K21 cp minus Ke cc. How does it come? R0, that is the rate at which the drug is administering into the central compartment. Here with this equation we are calculating only the change in plasma drug concentration in the central compartment. So central compartment, towards the central compartment we are administering the drug, from the central compartment distributing towards the peripheral compartment, and from the peripheral compartment drug entering into the central compartment, and from central compartment drug is eliminating out of the body. So the equation that represents the rate of drug administration, rate of drug entering into the central compartment is represented by R0. Then drug is moving from central to peripheral, there is decrease in concentration represented by minus K12 cc, that is movement of drug from the plasma from the central compartment into the peripheral compartment, K12, based upon the plasma concentration of the central compartment. Then back movement of drug molecule from peripheral into the central compartment. So this may increases the plasma concentration in the central compartment. That means movement of drug from the peripheral to the central based upon the rate constant K21 and based upon the plasma concentration C peripheral, that is concentration the peripheral Cp minus KeCC, that is drug concentration is decreasing from the central compartment. So this is the general representation of plasma drug concentration, change in the plasma drug concentration in the central compartment. Now, upon integration of the equation, you will get C is equal to R0 divided by VCKE into 1 plus, open the bracket, Ke minus beta divided by beta minus alpha into e raised to minus alpha t plus Ke minus alpha divided by alpha minus beta into e raised to minus beta t. Okay, so this is the equation what we are getting after integrating the previous equation. Okay, now so we have few some of the micro constants here, that is alpha and beta. Vc, as you know, that is a plasma volume of distribution in the central compartment. Alpha and beta are the two micro constants. This you already learned in two compartment IV bolus. Two compartment IV bolus. Okay, so Krishna Priya, you can answer what is the equation for what is alpha and what is beta, what is alpha plus beta, what is alpha beta, etc. Krishna Priya can answer. Okay, now so after integrating the previous equation, this is our answer. Now you think in this way, Ke minus beta divided by beta minus alpha into e raised to minus alpha t. So e raised to minus alpha t is an exponent that representing the distribution, and e raised to minus beta t is the exponent that represents the elimination. So in IV infusion we have two main rate constants, or the two exponents. It's a bi-exponential equation for two compartment IV infusion. The two exponents are the exponent for distribution and the one is exponent for elimination. So in the steady state concentration, you know very well what is steady state concentration. That is the rate of administration becomes equal to rate of elimination. Rate of administration becomes equal to rate of elimination. That is, in the steady state concentration, R0 becomes equal to K, or K becomes equal to R0, and then there is no further change in the concentration from the central and the peripheral compartment. So at this stage, both the exponent minus beta and minus alpha remains the highest value, and at the steady state concentration, these two things become zero. Which one? That is e raised to minus alpha t and e raised to minus beta t. These two terms become zero. Finally, you have the equation that is CS is equal to R0 divided by Vc into K. This happens only in the steady state concentration. So the C can be rewritten as CSS, that is steady state concentration is equal to R0 divided by Vc into Ke. Again, this equation can be modified as R0 is equal to CSS into Vc Ke. R0 is equal to CSS into Vc Ke. Okay, now this is a graphical representation. Just look into the graph, that's all. Okay, don't go through the formula and what is written. Okay, so this is a representation of an IV infusion. So drug is slowly representing entering into the body. It attains a steady state concentration. So once you stop the administration, once you stop the rate of administration, the plasma drug concentration gets declines. The plasma drug concentration gets declines. There is no further increase in the plasma concentration. Okay, now how to determine the elimination rate constant from the equation? Now, for an IV bolus, if you consider this same graph itself, IV bolus, we are administering the entire amount of drug in the systemic circulation. That means it's not time the complete amount has reached in the systemic circulation. There is only further decrease in the plasma concentration happens from a higher concentration to a lower concentration. What is the initial concentration? From that initial concentration, the drug is always declining, and there is only what? There is only elimination. So in order to determine the elimination rate constant here also for the IV infusion also, now currently our plasma concentration is also remaining in the maximum, that is in the steady state. Okay, from the steady state, if you want to determine the plasma drug concentration, the initial concentration is considered as the steady state concentration. For an IV infusion, in order to determine the elimination rate constant, the steady state concentration is considered as the maximum concentration, obviously. Now, so for an IV bolus, the equation is C equal to C0 e raised to minus K8. That is one compartment IV bolus equation is equal to C equal to C0 e raised to minus KET. Okay, so this equation can be rewritten. Instead of C0, you can rewrite as what? CSS for two compartments. So C equal to CSS into e raised to minus KET. Upon solving this, you will get what? You will get the equation for you can determine the value of elimination rate constant Ke. Okay, that's it. Okay, so even though if it follows a two compartment model, what happens? Even though it follows a two compartment model, after attaining the steady state concentration, that means at the steady state concentration it attains a distribution equilibrium. So once the steady state is attained, further if there is no rate of administration of the drug, there exists only what? There exists only the elimination Ke. This elimination rate constant can be determined from the equation for IV bolus, that is one compartment IV bolus. Okay, so this is a summary of this two compartment open model IV infusion, and here is the table. So for IV infusion, again it's a bi-exponential, and we have four rate constant R0, K12, K21 as well as Ke.